week having Matt Roberts visiting us from Chicago, and I guess he's going to talk about non-relativistic physics, non-relativistic spacetimes.
Right, thank you. It's a great pleasure to be back here in this lovely new building. I was not here the last time I visited. So I'm going to be talking about non-relativistic physics, non-relativistic spacetimes. This is based on two papers that came out earlier this month with two students in Chicago, Kartik Prabhu and Michael Garaci. So what I'm going to be telling you is basically a story of, if you are interested in a system that is non-relativistic, so you don't have to worry about, you don't have photons anymore, but you want to keep around Galilean boosts as a symmetry, right? Galilean boosts is a statement that even if you take c goes to infinity and you think about Lorentzian boosts, you still have a residual symmetry, right? There's a choice of what inertial frame you work in. And Galilean symmetry is just the statement that you want your physics to be independent of choice of Galilean frame. All right, so it doesn't matter if you drop a penny sitting here right now or you drop a penny while standing on a bus while it drives in a straight line, it still falls straight down and it looks the same. That's all the Galilean invariance is. It's actually the version of relativity that we're really actually familiar with in our everyday lives. And so, right, this statement is very simple. It's just, you want physics to be independent of a change of frame. And so what is that change of frame? Well, when I've taken c goes to infinity, well, okay, I can, of course, rotate my spatial coordinates, or I can boost. Sometimes this is called v, which kind of call it k. This is just how much I boost, right? So I go from a frame to a frame moving with some relative velocity k. This is just the change of coordinates. This immediately falls out of if you just write down the Lorentz group and you take c goes to infinity, you see that this transformation remains. And in fact, when you actually take the proper c goes to infinity limit of the Lorentz group, you get what's known as the Galilean group. The Galilean group is just, well, it's just rotations and boosts, so there's SOD, and it's non-trivial product with the boost part. Now this is what fell out of the Lorentz group. If I instead started with the larger Poincare group, so I just kept all of my translations, you actually get what's called the Bargmann group, which is just the Galilean group semi-direct producted with translations and an additional symmetry that's going to be particle number that falls out along as well. This is just a central extension. This is a full list of the algebra. It's kind of messy. The only things I want to point out specifically are, so here, right, J are spatial rotations. I have time and space translations. K is, again, the generator of boosts. And M is the central extension. You see that M is the central extension not of the Galilean group, but only of the Bargmann group, because you take the commutator of a spatial translation and a spatial boost. And I see that it can be centrally extended, preserving the rest of the algebra. And this is, when you look at quantum mechanical systems, for instance, M is the mass or the particle number of the system, which you would like to be preserved. Right. Okay, so this is a statement about flat space, right? And I've just written down, an analogy with how we write down Lorentzian boosts in flat space, right? But as I said, I'm interested in more general spacetimes. And in more general spacetimes, we don't actually have a notion of global coordinates that are preferred. Here, this is a statement about some preferred coordinates. Let me make a quick aside, and I'm going to kind of throughout be making analogies with Lorentzian physics and where things line up nicely and where things don't line up nicely. Okay, so why am I actually interested in kind of more generic curved spacetimes? If you really have a non-relativistic system, you would think that at worst, maybe you have to take into account a gravitational potential in an actual laboratory system. But that's it, right? You're never going to have some really complicated non-relativistic spacetime. I mean, you have to go out and look at, solar system scales to see non-trivial actual Lorentzian spacetimes in real life. So why do we care about this? And the reason we care about it is the following. If you want to require that the mathematical construct that you use to make predictions enforces your symmetries, there's a very easy way to do that. So for instance, if you're interested in a quantum field theory that's Lorentz invariant, and you want to study a bunch of transport, for instance, you want to calculate stress tensor correlation functions. Well, you know that there is an operator that's defined as the stress tensor. It's the Noether current for translations. And you can just take that operator calculate a bunch of correlation functions, and it gets very gross very quickly. You can, at least theoretically, do something that's a little more slick, right? So you know, how do you do that coupling? You say you have a partition function, and, well, there's some, just whatever my microscopic fields are, and then I'm just going to add an additional coupling term, H mu nu, T mu nu. Now I know that Z is a function of H, and if I take functional derivatives with respect to H, I get stress tensor correlation functions. I'm not saying anything astounding, right? But this is just a statement at the linearized level, and if I'm interested in nonlinear response, I can very simply generalize this to saying that I'm actually going to study my quantum field theory on a generic Riemannian manifold, where now that was just a linearized approximation to I actually have some matter fields that are coupled to just some generic space-time metric. There could be other stuff in there as well, but this is very generic. So once I've done this, I'm allowed to write down a bunch of new terms, right? So maybe previously I had partial phi squared minus m squared phi squared. Well, once I have a metric, the first thing I do is I turn these into covariant derivatives, because that's the only derivative that makes sense. And this is what's called minimal coupling. But I don't have to stop here, right? I can write down other terms, right? I could write down, a coupling, a mass term that looks like a mass term, except it couples to curvature, et cetera, et cetera. So coupling to a generic spacetime is not in any sense unique. But if I take a particular power counting scheme, I can just algorithmically, order by order, see all of the terms that I can write down and enumerate them. Okay. And so this is an extremely useful object because now I know I can do all sorts of nonlinear response questions and, for instance, take a bunch of derivatives of z with respect to g at different points and get a bunch of stress tensor correlation functions, right? So, it's a useful mathematical object if you're interested in studying, say, particular types of energy transport or momentum transport, stress, strain, etc. So this is how things work in Lorentzian spacetimes. Now we're interested in non-relativistic physics, so we want to know what is the appropriate analog of a Riemannian manifold, or a Lorentzian manifold if you want to always be specifying that it's of the right signature. Okay. Well, a perfectly reasonable guess would be just Newton-Cartan spacetime, by which I mean the appropriate covariant description of Newtonian gravity. So in Newtonian gravity, the only real additional data you have is that there is, instead of a full space-time metric, there is, really just what is effectively the lapse of the Lorentzian manifold. There's a Newtonian potential, and the Newtonian potential moves mass around. It doesn't move energy around, it moves mass around because it's a non-relativistic system, and those two things are now explicitly distinct, right? So there's nothing wrong with doing that, and there's a very nice literature. It's very pretty. The problem is the following. If all I ever include is the Newtonian potential, then this type of story that I unfortunately erased will only let me calculate mass transport. And if I want to study something else, like strain or energy transport or charge transport, I need something that couples to those things, in the sense that, we usually say in the Lorentzian system, ds is, well, up to some factors, right? There's the stress tensor times the progression of a metric, right? So this is what happens in the Lorentzian case. And unfortunately, if all I have is a Newtonian potential that I'll call, say, phi, all I'm going to get is a mass density. And that's just, that's not enough. We want to have more general transport. So I need to figure out, well, what are the other terms I want to vary in there, right? So for instance, I want to have some energy density. I want to have an energy current, a momentum current, et cetera, et cetera. And I need to know what the appropriate geometric object I put in there so that I can do this linear response story. And the answer is basically going to be a large generalization of the old story about Newton-Cartan spacetimes to include a whole bunch more mess. Are there any other questions about the motivation before I kind of dive in? Great. Okay. And again, this may kind of get very mathy very quickly, so if it goes too fast, please stop me. Right, okay, so this is a statement about what boosts look like in flat space. In curved space, we don't have that, right? In curved space, at best, we know that at a point in spacetime, we can ask for a basis of frames or coframes. Frames or coframes is basically a basis for vectors and one-forms at that point in spacetime, right? So if I had a set of, say, coframes, that would just be dt and dxi, for instance. I'll write them as E, A, mu. Greek indices are always actually going to be space-time coordinate indices, and Roman letters will be group indices. So here, A runs from 0 to D, or I'm imagining my space-time is D spatial directions in one time direction. Okay, and the trivial generalization of that is that this set of frames, where I'm going to write this in components E0 and EA, these are forms, and now I'm going to assume little a goes from 1 to D. So this is just the spatial group index. Under a boost, this just rotates very simply. Get these right. So this is just a boost and a rotation. And this is just an element of the Galilean group, right? This is really just a kind of local space generalization of this. All right, and this, in fact, is going to define the fundamental, well, really, this is in the fundamental representation of the Galilean group. I've broken this in components in a particularly nice way. So this is a bunch of coframes. Now, again, if we were, for instance, doing Lorentzian physics, I know that I have some special preferred tensor eta, which would be, -1, 1. And this is actually invariant under gauge transformations. And so I could take the coframes and turn them into a space-time metric, right? But it's easy to see that if I think of this, what group this is, eta is just, it's no longer an invariant tensor. There are, in fact, only 2 invariant tensors that you can see in this representation. There's one, that's NA, which is just 1, 0, right? That's just the statement that this 0 component obviously doesn't change under this rotation, okay? Now, I don't have a space-time metric, but I can define a two-sided inverse of these coframes, E mu A. So now this is a dual fundamental, in the dual representation, and it's a 1, 0 tensor instead of a 0, 1 tensor, such that E dot E is a delta function, and it's a delta function in either the gauge index or the space index, depending on which index I contracted. This guy exists and is unique so long as this, as a matrix, is not degenerate. Okay, so I have this guy here, and so then, if I think about things in the dual representation, I see that I also have the following invariant tensor. This guy, right? Because it rotates, but both indices rotate and they cancel. Okay, so in terms of space-time data, this tells me that on space-time, I actually have an invariant object, n mu of one form, that's n, a, e, a, mu, and this gives me a degenerate thing that looks like an inverse matrix. Right? So these two guys are just explicitly invariant under local rotations and local boosts. The boost part of this is often called the Milne boost, and I may end up using that terminology. When I say something is invariant under boosts, I don't mean a coordinate transformation that looks like a boost. I really mean this part of a gauge transformation. Okay? So these two guys are invariant, and this is actually where most stories about Newton-Cartan geometry start. They say, on your spacetime, you have 2 invariant tensors. One is a 1 form, and this 1 form, and this, okay, and then obviously h dot n is 0, so you also get that in the spacetime objects are orthogonal. Okay.
Excuse me.
Yeah.
You're saying there's no epsilon tensor invariant?
Oh yeah. So that's another invariant. Well, that's an invariant under simply connected parts, right? If I do a reflection, it is an invariant under that. But yeah, of course, yeah, I'm sorry. Yeah, there are a bunch, right? There's A0 to AD. There's also in the dual representation, and these give me volume forms. You're absolutely right, sorry, yeah. No. And then once I have this guy, I can use N to project this to a spatial, not a form, but a spatial antisymmetric guy. But I can't get a spatial form that's invariant because N is really in the dual, not in the fundamental. Right, okay. So yeah, so thank you for that question. Okay, so usually people start with this, and let's talk for a minute about how we physically interpret these things. So N.
I'm sorry, did you say that both the Greek and the capital indices go from 0 to D?
Yes, but Greek indices are coordinate indices, and capital letters are the basis. Yeah. Right. Okay. So N is a one form, and it's called the clock form. It's called the clock form for the following reason. It defines a notion of elapsed time. If I have a curve, I can tell you what the elapsed time along that curve is by just integrating the pullback of N along the curve. Right? It also defines a notion of spatial vectors. Right? If a vector is annihilated by N, we call it spatial. It's not something too surprising. Now, you might ask, well, if I have a whole set of spatial vectors, can I integrate them into a codimension 1 hypersurface that I can think of as being at constant time? And of course the answer is not always, right? The question of whether or not you can integrate a one form into a codimension 1 surface requires the Frobenius condition. So I'm going to erase some of this over here. So the Frobenius condition is right. So the question is, when you have a one form, when do there exist, at least locally, hypersurfaces orthogonal to it? And that requires n wedge dn equals 0, right? If n wedge dn equals 0, Frobenius proved that you can write that n is of the form alpha dt for some coordinate t, at least locally. For the bulk of this talk, I'm not really going to worry about global topological issues like orientability of these surfaces, right? You can imagine you have something like a Mobius strip, where I have n pointing forwards, but I go around some non-trivial cycle and it ends up pointing backwards, and I'm in trouble. I'm only really interested in local structure. If n is of this form, then I know I have the following picture. Okay, here's t equals 0, here's t equals 1, right? So as long as this is satisfied, and this is what we call the causal condition, there exists a global notion of time, in the sense that n is written in this form. Okay. But there isn't really a local notion of time necessarily, right? Imagine the following experiment, okay. So once n is of this form, I have a notion of things being simultaneous, right? If 2 points can be connected by a spatial curve, which means that there's no elapsed time along it, I say that they happen at the same time. And in fact, there's a very nice theorem that says that if n wedge dn is non-zero at a point, then there exists a neighborhood about that point within which any 2 points in that neighborhood can be connected by a space-like curve. Which just means that if n wedge dn is non-zero, I really have no notion of causality. Now this seems very strange, right? In Lorentzian physics, issues of causality are always global, and that's because in Lorentzian physics, we have light cones that you can always conformally rescale to put at right angles away from singular points. But when you take a non-relativistic limit, you send c to infinity, and that means that you've opened up the light cones maximally. What that means is that if I look at the next surface just barely ahead, every point at t equals epsilon is in the future light cone of any point right before it. The causal structure is just totally different, but it's really what you expect, right? You have instantaneous propagation because you took c to infinity, so anything that can propagate information is moving infinitely fast with respect to how you measure velocity. Right, so the causal structure is kind of very different, but that's okay. But so this is the data that's in n. N tells us about how time behaves. Now, you might think, well, I can define the following object, for instance, H mu nu. That's going to be delta AB, E, A, sorry, E. So again, these indices are purely spatial. I can define an object that looks like this. Now, even though I've written it without any group indices, this is, of course, not invariant under boosts. But you can show that this object, when pulled back to a t equals constant hypersurface, is invariant under boosts. And that's the sense in which H is a spatial metric, right? So in this structure, if I can define constant time surfaces, there exists a spatial metric on those hypersurfaces, and it's non-degenerate, and it's positive signature. Okay, so that's what the group looks like. And we talked about causality. Yeah. So right. So yeah. Okay. Now, right. I just told you that these are the only two objects that are invariant under boosts. And now we're talking about non-relativistic physics, so we realize that we are immediately in a whole heap of trouble if we try to write down the Schrodinger equation, or the Schrodinger action, right? So what is the Schrodinger action? Well, there's a kinetic term that I know is going to be basically Hij over 2m. Let's just make these partials, right? And this part is easy, but we don't have the time derivative, and the time derivative in the Schrodinger action is really a time derivative, which means that what's secretly living here is something that looks like a time-like vector. And we just argued that this object doesn't exist, right? What this would be in my coframe notation, frame notation, would be E0 mu, and it's easy to show that this object transforms under boosts, right? So what do? Right? We need something to fix the fact that under boosts, I erased it, but V mu goes to V mu plus H mu nu K mu, right? In my construction, I didn't say it, but with this definition of V is always normalized to be plus 1. Okay, so this is a reasonable definition, but it's not invariant under boosts. So what do? Well, people have known for a while what you do. You have to covariantize this derivative with something that transforms very strangely. And so when people first started doing this, they say, well, if it's the Schrodinger field, maybe it's charged and there's a U1 connection, so you say that your partial derivative turns into a covariant derivative, which is partial minus I A mu. I'm writing this as little a because there's been confusion in the literature about whether this is an electromagnetic gauge field or not. It is not. This is some different gauge field that we're going to see is related to U1 mass. And the transformation property we need is that A, under the boost part of the transformation, A goes to A minus plus K mu minus a half K squared N mu, where K squared, anytime I have a tensor and I square it, it's actually squared using this guy, right? Now, it's an unenlightening exercise to go through and say that if I correct my derivatives in this way, and I turn this into a covariant derivative, and I turn this into a covariant derivative, that this action is in fact boost invariant. It's not obvious, but it's it's important that this transformation is nonlinear. But you can show that this is invariant. It's not super exciting, but it's a straightforward exercise. And that's
Sorry.
yeah.
So is that establishing local invariance or?
Yes, this is local invariant. So this is equivalent to saying that it's invariant under, in the Lorentzian system, you can require something to be invariant under local Lorentz transformations.
But before you didn't even have global, or did you?
No, I didn't have any invariance. But now I have, global is a subset of local, but yeah.
I just find it a bit strange to introduce it. I mean, if you would want to introduce just global invariance and try to avoid.
The point is that, I can make this global by just looking at only cases where k is constant, but I'm still dead in the water, right? And in particular, it's worth pointing out, this is not a gauge, this is not like a U1 gauge transformation, right? A is not shifting by something exact. It's shifting by k, right? The same way that V shifted, right? So this is not like a U1 correction. This is something really different, okay? And in particular, it's maybe not obvious, but you can actually fit these guys together into a different representation, the extended representation of this group, which is the following. So let's just define an object, EI mu, which is going to be N, EA, and little a. Now I is going to run from 0 to d plus 1. So this is just some extra piece. And now let me get the transformation property right. Well, yeah. So this transforms, if I package all of this together, I can show that these guys are transforming with the following representation. Right, and this is what we call the extended representation. Now you notice it's the same group, right? The same data, there's just a boost and a rotation. But it's clear that E under these components, under the transformation rules I've written down, go to just lambda dot E, right? So this is just a different representation. You know, it's particularly nice.
So I'm
Yeah.
a little confused. What, maybe you said this, what is Kmu?
Kmu is K.
Okay, so mu
Boost
runs-
parameter, right?
It's a boost parameter, yeah. So as I switch between here,
Yeah.
I'm thinking of it as an element of the, you know, this is a parameter for the group element, but I can, using the coframes, I can turn it into a space-time tensor. That's all. I'm just kind of hopping back and forth because, you know, if I have to write out every time I change an index from one type to another, it just gets very cumbersome very quickly. But it's just the boost parameter.
I was just confused with the running from 0 to d versus 1 to d. But-
Yeah, no, so it's right. So this is the zeroth component.
Yeah.
This is the 1 through d, and this is the d plus 1 component, which I'll sometimes call kind of the mass component, because as we'll see, it's related to U1 mass. Okay. Right. So this is very nice, and what will end up happening is, so this is this new object, this extended coframe, that we are going to eventually see is going to help us repair the Schrodinger equation into a workable form. Now the Schrodinger equation is a particularly nice example because the field is a spin zero field, so the derivative operator is very trivial. But a completely fair question to ask is, what is the generic derivative operator? How do I, you know, if this is supposed to be a manifold, I need a notion of parallel transport for tensors. And I haven't told you how to do that yet. I'm surprised no one yelled at me when I wrote down D with only partial derivatives. But yeah, so we need a derivative operator, right? And what do we want? We want a derivative operator that's compatible with our spacetime object. So we want the derivative of n to be 0 and the derivative of h to be 0. Yeah?
Before you go on,
Okay.
you called n the shift
N is the clock form. When you do an ADM decomposition, n is going to be related to data in the lapse and the shift. But
both of them.
I mean, generically, yeah, right? I can, well, yeah. The lapse and the shift are not defined invariantly. I can always do a boost in the Lorentzian system and mix them, obviously, because it depends on my choice of t.
Okay.
Hopefully I'll have to that. So we need a derivative operator, and we want it to satisfy this. But what is a derivative operator? When we do frame bundles and co-frame bundles, a derivative operator, it's easier to not work with Christoffel symbols, and we'll get to it eventually. It's easier to just work with the spin connection, or really, in this case, since these objects are in the Galilean group, we need a Galilean algebra valued one form, and that will be the Galilean connection, right? And so let's decompose it, right? So it's supposed to be Galilean valued. So if I write it in the fundamental basis, I'm going to suppress the fact that this is a one form. It's just 0, 0, this guy, this guy. So this is the Galilean connection, again. So there isn't this component, but this component survives C going to infinity. This is what we call a boost connection. And this is just the usual spin connection in the sense that this is the connection for the SOD part. Remember, The Galilean Group is just rotations semi-direct with boosts. So we can identify the spin connection part pretty simply. Okay. And now this gives us a totally nice notion. I can also define this in the extended representation. Right, it's easy to work out what it is. And all you do is you end up adding a few more lines. Right. So there's the connection in the extended representation in case someone wanted it. But great, so now we have a connection, so we can define derivatives very simply. Right? We just use the usual story, which is, okay, if I have some, let's just start with a form that's valued in, for instance, is in the extended representation, then its covariant derivative is just going to be the usual covariant exterior derivative. And then using the product rule, this tells us how to take derivatives in any kind of tensor product of fundamental and dual representation. Then similarly, if you want to work in the fundamental representation, i's and j's turns into capital A's and B's. But this is it. This is our derivative operator. And it's not obvious what all of this information is in it. But right now we can start doing geometry the way we like to do geometry. For instance, I have a covariant derivative operator, and I have something that looks like a coframe. Now we should be nervous when I call this a coframe. It's not a square matrix. It's not invertible, so there isn't an inverse extended coframe. But I can now, for instance, define, well, let's start with the easy one. Torsion, right? What is torsion? Torsion is just the covariant derivative of my coframes, right? So you know what this is. It's just this formula here, right? I can also define curvature. All right, and what is curvature? Well, it's just usual formula, right? So this is just Cartan structure equations, nothing exciting and new, but it's clear from this that we have a good notion of derivative operator. Now, since these guys have non-trivial indices, I can point out the following statement. I can say, well, let's think about boosts, for instance. So under boosts, how does torsion transform, for instance? And in a moment, I'm going to try to tell you why we care about how torsion transforms. All right, so this, well, first of all, what are the components? Well, one of them is dn. The next one is just so let me point out a few things here, and I'm suppressing a bunch of spatial indices to make things a little quicker. So the zero component of the torsion is just how not closed n is, right? And there's spatial torsion that looks like the usual formula for spatial torsion, except for this additional part, right? Remember, these are the spatial frames, and this is the spin connection, and it's modified by something a little different. And then we notice that the kind of d+1 component looks like a field strength for little a plus something else.
Excuse me.
Yep.
Did anybody try to get this from a higher dimension? I mean, adding one dimension seems quite natural there because you have...
Yeah, so I'm not going to go into it in detail, but of course you can get this, well, it's related to a null circle reduction in the usual story, right? So I can take C goes to infinity to get Bartman, or I can look at a null circle reduction on one higher dimension. There are subtleties and things here. Okay, and so I can tell you that Ti under a boost goes to, well, dn doesn't change. This component shifts by dn. Right. So if, right, we know in Lorentzian geometry we don't usually like torsion, so if I want to turn off torsion, well, if I set dn to 0, because dn is an invariant, then the spatial torsion is invariant, and I can then say, well, if I set dn to 0, then I can invariantly set spatial torsion to 0, and then if I set spatial torsion to 0 as well, I can set this mass torsion to 0. But generically, they're all mixed up. Now, this is a problem, right? This dn part is a problem for the following reason. There's a very nice paper by Luttinger that makes the following argument. So if you assume that n dn is 0, that means that I can write n in the following form, e to the minus phi dt in some coordinates. And there's a really nice argument by Luttinger that I don't want to get into because it's a little messy. It's just kind of, but it's true, that if I'm interested in thermal gradients in some system, right? So in a Lorentzian system, if I want to look at a static thermal gradient, I think of the system as a Euclidean statistical system, and then I change the size of the temperature circle, because the size of the temperature circle tells me I've redshifted the locally measured temperature, which is the same as putting it in the thermal gradient, right? And similarly here, Luttinger argued that the gradient in phi can be related to the relative gradient in the temperature. So, right, and this is a statement that, right, in non-relativistic physics, thermal gradients tell us that energy moves. So this potential here, which is often called the Luttinger potential, is what we need to turn on to study energy transport. But this argument just here told me, well, if this guy is non-trivial, if it has a gradient, then dn is non-zero, obviously, right? Because it's just d phi which dt. So if dn is non-zero, I have to turn on temporal torsion, which means I have to turn on all torsions, right? So there was a special case buried in here that I didn't tell you about, that is, if I set all of the torsions to 0, this just reduces to Newtonian gravity. And I can go through that if people want to see. But if I want to study energy transport, I cannot just look at Newtonian gravity. I need to look at this whole horrible, complicated mess. And it's not that bad. So this is actually the system we want to look at. Okay, any questions?
Can you at least put some constraints on the torsion? I mean, what would be the nonce?
I can't put invariant constraints, right? If I pick a particular system and don't mind picking a gauge, then I can impose whatever constraints I want in that gauge, but they're gauge dependent, and so they're not particularly physically useful. And it's better to think of things that are only gauge covariant, because then we can talk about things like Ward identities, etc. Right. Okay, so this is the structure. You can do the usual story of going from the spin connection to the Christoffel symbols. I've wrote them out here. It's not particularly enlightening. Yeah, let's see. In the interest of time, skip over a few things here. All right. So let me make a quick comment. All right. So a useful way to understand what manifolds look like, or geometries in general, is to ask questions about geodesics. Right. So what do geodesics look like here? Well, it's pretty simple. Imagine I have some curve parameterized in the following way, and then I define the unit normal vector like this, right? Now, I didn't tell you this, but it turns out that in the extended representation, there's actually another group index that I should have written down. This guy. This is a group invariant in the extended representation index. What it basically gives you is something that looks like G mu nu is H mu nu plus N cross A. Which looks great, and it looks like we almost have a spacetime metric, but of course, this is not always invertible, so it's not actually a spacetime metric. It's also not gauge invariant with respect to little a, but we'll get to that later. Okay, but thanks to Gij, and this guy is of course invertible, and it has signature -1 and then a bunch of pluses, and this will not surprise you that this is in fact related to getting this out of a null circle reduction, because this is just in light cone coordinates, a higher dimensional space. But I can write down the following action. Right? And ask, right, and this is meant to be in direct analogy We're in Lorentzian spacetime. I would say I have an action that's just going to be m over 2 times, G mu nu C mu, right? But here, this is actually a spacetime metric, and these are unit normals. And this gives us the geodesic equation. At least without torsion, right? So this is the Lorentzian story. This is a useful action. It gives us the geodesic equation. And it turns out here, I don't get the geodesic equation. You get almost the geodesic equation, except torsion is a force. Right? So it's clear from this equation that if I set all of the torsion to 0, not just temporal and spatial, but also this extra mass torsion to 0, then my geodesic equation is just the usual geodesic equation. And that's why it's Newtonian gravity. There's a reasonable sense of equivalence principle, right? This is just the geodesic equation, and if Ti equals 0, you can, in fact, identify things so that this equation is the same as x double dot I is just partial I phi, right? So this is just the geodesic equation and the Newtonian potential. I'm not saying anything too exciting. But generically, it is not Newtonian gravity. It is something different. Yeah?
Sorry, will there usually be the square root of the point?
Yeah, I made an assumption that these guys are unit normalized, so it's the same. But yeah, sure. Right, it's both are reparameterization. Well, sorry. This is reparameterization invariance. I picked a parameterization. I said it was affine unit, and then it's the same. Yeah. Okay. So. Okay. All right. Well, we can do better than that, right? Because thanks to this guy here. Well, so this nicely gave us geodesics. We can actually do better, right? So I told you that we'd be able to write down Schrodinger's equation invariantly in a very compact, nice form. And you can. The only thing you need to do is the following. I'm going to say I'm going to have a derivative operator again. So d mu is going to be partial, which is the same as a covariant guy on the scalar fields, minus I a m, right? This was the thing we had to put in to write down Schrodinger's equation. So I think that was correct. Yeah. Okay. Now, it's perhaps not obvious that the components of this transform in weird ways, right? So if I say d0, using the frames, under boost, this goes to d0 plus ka dA minus a half k squared m, etc. So this derivative operator does not look like some nice object. So the point is that d mu, e mu a, isn't something that transforms nicely because of this junk I've thrown in here. But I can define a better derivative operator, di, in the extended representation. There's the 0 component, spatial component, and the mass. And again, this is the part where you should realize that this looks awful lot like a null circle reduction, right? This is the momentum in the null circle. I mean, it is basically that. And so this guy here, you can easily show that di goes to, well, lambda inverse d, right? It transforms in the dual representation as expected. So this is a good derivative operator. And then you can very quickly see that if I write down the following action, you expand this out using all the definitions I've given you. By construction, I know that, these operators transform homogeneously. This is an invariant. So this action, first of all, is explicitly by construction Galilean invariant. And also, it's just the Schrodinger action I wrote down previously, right? I've mixed the K's and A's and I's all cancel against each other extremely nicely. This is just the Schrodinger action. And now I've been able to define invariantly the Schrodinger action on basically any spacetime with all of the torsion I want. In particular, I can turn on a non-trivial Luttinger potential and look at energy transport in this theory. I can add other terms if I want to, et cetera, et cetera. The fact that these things line up is not particularly new, but the identification of this derivative operator and the extended representation, I think, is, at least to us, was new. So this is a nice object. So here's Schrodinger's equation. So, there's no longer this weird mystery about, I think I've erased it, this weird mystery of how I have to introduce this field, little a, have it transform in what looks like a very strange representation. It's just a different representation. And everything works out very nicely. Okay. All right, so in the little bit of time I have left, I'm going to try to make a few more points. Are there any questions about this? Great. Okay. So being able to write down an action is all well and good, but when you have symmetries, symmetries give you constraints, right? Symmetries give you word identities. And so what we really wanted to get is general word identities, right? And how do word identities work? You say the variation of the background data of an action defines a bunch of currents, right? So for instance, there'll be, J mu delta A mu plus, T mu nu delta G mu nu plus etc., right? These are the Noether currents for these symmetries. And then you say that, well, if the variation is actually a symmetry transformation, it's 0, and so there's some constraint, right? So for instance, in this case, you see, you get, so this is a Lorentzian statement, right? Right, and also, right, so word identities, right? We like word identities, they're good, they constrain systems. They're powerful tools when you're actually sitting down and doing a bunch of calculations. So this is what Lorentzian word identities look like. So the question is, what do word identities look like in our geometry? The symmetries that we have are, again, right, there are a bunch of translations, there are boosts and rotations, and there's this U1 mass. Something that I didn't say particularly explicitly is that this action as constructed isn't just invariant under Galilean boosts. It's also invariant under U1 mass, which is just mass or particle number, which is just psi goes to psi e to the I alpha, and A goes to A plus d alpha, right? And since in microscopic systems this just corresponds to conservation of particle number, it's a useful thing to want to require. In physical systems, it's usually true. Certainly in Galilean systems, it'll be true. You can't spontaneously break it. Okay, right, so that's an additional symmetry that we're going to have. But so first let me tell you what all of our actions are. So since we can now organize things very nicely, I can just write this as minus T U I Now here I've actually just, for fun, thrown in a charge conservation, a conserved charge. Charge and particle number don't have to be the same, so in this system I could have neutral particles and charged particles, and there's no problem. Everything plays nicely. So this is some weird object, right? It's not just the stress tensor anymore. I can actually decompose it. If I right, this horrible giant object is the following thing. Well, there's an energy density and an energy current. Okay. There's a momentum current. And there's also a particle number density, or mass density, and mass current. Right? Again, things they're non-relativistic, so these are decomposed in this way. So, and okay, this is spatial stress, energy currents, mass currents, and momentum current. There's no momentum density. Okay. Now, I know that I can do symmetry transformations that are either gauge transformations on this index, or diffeomorphisms, or if I wanted U1 transformations. And I'll get some word identities, and so you can just write them out. They're not super enlightening, but they're useful.
Excuse me.
Yeah.
As it's at the classical level so far, is it just Noether identities? I mean, when you're saying word identities, you mean Noether identities? Or
Yeah. Well, I mean, they'll become word identities when I make it quantum mechanical and take care of contact terms, but yeah. Yeah, it's the same thing in my language. Yeah. All right, so this is a big mess here, but basically what you're finding is this thing is the analog of the conservation equation for the stress tensor. Here, TAMU is a partial trace of the torsion tensor. That's what this is. So you have something that looks like the divergence of the stress tensor, and then there are a bunch of forces acting on things. So torsion acts as a force, electromagnetic fields act as a force, curvature acts as a force. This is the spin connection. I didn't point this out explicitly. So this is not just the usual non-relativistic spin current, but there's also a boost current component to it. Right? I have basically S mu 0A and S mu AB. This is the usual spin current for kind of non-relativistic spinning particles, and this is the current if I have a physical system where the fields I'm interested in themselves transform non-trivially under boosts. Now here, I actually made an assumption that no one called me out on, where under boosts, actually under the whole Galilean group, I assume psi goes to psi, right? Now I could have made them spinful and said that they actually go as e to the I, s dot theta psi. So this is if they're spinning particles, and these are the generators for rotations. They're spinful, but I also could put in a spin component for boosts. Now, as far as I know, there are no actual physical systems where the quasi-particles in your material transform non-trivially under Galilean boosts. But I don't have a proof that that's never an interesting question. We made that assumption when we did our calculations. So, right, so this is one word identity. Word identities, or their conservation rules, are important, for instance, if you want to ask about hydrodynamics, because in hydrodynamics the equations of motion are just the conservation equations plus an equation of state. And that's one motivation for looking at these things. I'm sure it's on that page. You can ask about boosts. Sorry, so I should be clear. This right, the conservation of the stress tensor comes from diffeomorphisms. I should have said that explicitly. Under boost, you can work out the following thing. So again, this is the boost part of the spin current. Now, this is a little surprising, right? Because there's this lore in non-relativistic physics that the mass current and the momentum current are the same, right? If you just have a bunch of particles and they're moving with some velocity, the mass is moving, so the momentum is just supposed to be P equals mv. So this is a little surprising that it's not actually just equal. There's something else here. But of course, if you have a field such that doesn't transform under boosts, then you know the boost current is actually 0. So I should say if fields don't transform under boosts, then you recover mass current equals momentum current. But I mean, and I should mention that there's a paper by, oh God, I'm going to embarrass myself and forget the name, probably Duval and company, that actually look at generic representations of the Galilean group. And there are representations that transform non-trivially under boosts. You can think of them as basically C goes to infinity of the spin half representation. But I couldn't find anywhere in the literature people actually using that for a microscopic description of some condensed matter system. It's something we're thinking about, but we haven't worked through the details yet. This is S0A. So, you know, in general, you get something different. But if fields are trivial under boost, then you just see, again, these two things are tied to each other. And lastly, you can ask about rotations. Rotations tell you that the antisymmetric part of the stress tensor is constrained by the spin current, right? And this should look very familiar to anyone who's looked at these ward identities in relativistic systems. This is basically identical to what you find there, right? Usually we say that rotational invariance tells us that the stress tensor is symmetric. That's, of course, not necessarily true if you have non-trivial spin currents. So, for instance, if you look at this, remember that when you start out trying to write down a stress tensor for a Dirac field, you do the naive thing where you vary the tetrad, and you see that you get an object that isn't actually generically symmetric. And there's a story about adding a Belinfante improvement tensor, and it is basically fixing this term here. And you can see that, you know, when you do the correction term, this in fact works out nicely. You get a conserved stress tensor. So this is just an analogous thing. Now, I should mention, so that story about Dirac is nice in the relativistic case. In the relativistic case, you know that you can either vary tetrads and spin connections independently, or you can vary space-time metric and torsion independently. And the right, well, you know, quote right, the standard definition of stress response is varying a metric holding torsion fixed, because response to torsion is something different. It's not really just squeezing a system anymore. Here we can't do that, right? Because part of the space-time data, for instance, is varying n, right, to get the energy current. But I can't vary n to get the energy current holding the torsion fixed, because varying n explicitly turns on torsion. So the usual story about varying, you know, tetrads and torsion versus tetrads and spin connections doesn't quite work here in an appropriate invariant fashion. I'm running short on time. I can just say a few words. Well, yeah. So something that I don't have time to get into too much detail is, this is nice. We've enumerated the full set of conservation laws consistent with these symmetries. So then a natural thing to ask about is, for instance, non-relativistic fluid dynamics. And what you end up doing is the usual story. You write out some constitutive relations. So we do. So how do fluids work? I say, well, I have a bunch of thermodynamic variables, like a temperature, let's say a chemical potential. This is a chemical potential for mass or particle number. And I have a fluid velocity, u. And then all I need is an equation of state, like pressure as a function of temperature and mu. And I get some hydro equations, and so I can just tell you what they are. So it's a 0th order. So this is the covariant mass current. So, right, in equilibrium, what do you expect? You expect that this is the fluid velocity. So the mass current should just be going with the fluid, and the energy current should just be going with the fluid, with the mass and energy densities respectively. And this is really just pressure and strain. And so it is just pressure times the spatial metric, right? And you can, so you take, this is your 0th order data, you have an equation of state, and then you look at these ward identities that I've written out in in some horrible formula, you plug this into them, and you get some nice equations of motion, which are just Navier-Stokes and continuity, conservation. Write this down and I can tell you what it is. Okay, where? So first of all, dotted objects are u derivatives. So it's just u dot grad of that object, right? And so theta is the expansion, and alpha is the acceleration of u. Little e is effectively the electric component of F. So you remember I had this background field F. Well, okay, we should just set that here. Doesn't matter. This is an electric field. Effectively, this is a torsion component. Or again.
If I want to consider viscosity, I have to add something more.
Sorry, what?
Viscosity.
So viscosity is first order anticipation. This is perfect fluids. Right, so these are just the perfect fluid equations of motion, yes. You can work out viscosity as well. It's just some first order data. You can, for instance, show that the shear and bulk viscosity have to have particular signs to satisfy second law. But in 2 + 1 dimensions, there's a parity odd viscosity channel called Hall viscosity, and that doesn't have to have a particular sign. Yeah, I mean, it's. I can tell you about our results at first order anticipation, but it would be basically a list of things and telling you whether they are 0 or they are positive or negative or just something. And without going into details, it might not be particularly enlightening. But yeah, you can work out viscosity, you can work about conductivities, etc. Yeah. So I think in the interest of time, I will wrap up. So these are the perfect fluid equations. You can go to first order. I just want to mention a few kind of open thoughts. I didn't have a chance. So I didn't say this explicitly in detail, but for instance, if you want to get a non-relativistic spacetime as a c goes to infinity limit of a Lorentzian spacetime, you can do it, and we did it in our paper for the following particular example. If you set spacetime torsion to 0, then you just do an ADM decomposition, and the lapse and the shift tell you what little n is, and that's where the Newtonian potential lives. And the spatial metric in the ADM decomposition is the spatial metric, right? That's not particularly surprising. And in particular, I just want to say something quickly. You can ask about, can you go from something like Klein Gordon to Schrodinger? And we of course know we can't, right? I'm not saying anything new or surprising, right? How do you go from Klein Gordon to Schrodinger? Right? It's simple, at least in flat space, right? You say my Klein Gordon field is actually just E to the minus I m c squared t psi. You plug this into Klein Gordon. You take c goes to infinity. You see that this cancels the c squared part, and you're left with Schrodinger, right? This works great. Okay, when can we actually do this in our generic curved spacetimes? We can only do this if dn equals 0, right? Why do we need dn to be equal to 0? It's a question of what this t is, right? Remember, if I have some generic spacetime, I don't think I actually wrote this down. I should have. I apologize. If dn is not 0, I'm assuming that n wedge dn is 0, so I have constant t surfaces. Now remember, n gives me elapsed time. So here's a curve, right? So this is t equals 0, and this is t equals 1. Now, here's a curve. This part is on the surface. So here, there's no time, and here, there's no elapsed time. But there's an elapsed time here and an elapsed time here, right? Now, so this is another way of saying, how much time does this guy see relative to how much time this guy sees? And the answer is simple, right? The integral of n along my curve is, of course, the integral of the flux through it. So if dn is not 0, different observers see different elapsed time. And then I'm in a great deal of trouble, right? Because if different observers see different amounts of elapsed time, I don't know what time function to put in here. Now there are other issues because, for instance, I need to figure out, if dn is non-zero, that actually means that, as I've argued, there's torsion, and so I need to do a whole lot more work. But an interesting open question is, can we take appropriate non-relativistic limits to get kind of more generic spacetimes that have, right, this is basically saying there's a non-trivial Luttinger potential. So to get a non-trivial Luttinger potential, you don't have globally, you don't have different observers seeing the same amount of elapsed time, and so the usual non-relativistic limits don't work out nicely. So that's something we'd like to understand better, but we don't yet. And I'd like to call, in the interest of time, I'll wrap up. Thank you.
Are there any questions?
I once knew the answer to this, but I forgot. Let's go back to the case where n is 0, and you can reduce Klein Gordon Schrodinger nicely. Where does the non-central extension come from? Well, the gray group doesn't have any non-trivial central extensions, right?
Yes, so that's a good question. The answer is basically that you think P0, when you do the large C expansion, you basically say there's H plus M over C squared. So if I decompose this generator into these two pieces, and I take C goes to infinity, I see if I kept track of this, I found the central extension. So it's just in here. It's not obvious, but it's true.
Okay, out there.
Yeah. I mean, I can show you in much more detail later, but yeah.
We don't have time. Don't have time for that.
Yeah.
Any other questions?
Is this model supposed to describe actual condensed matter systems in 3+1 dimensions, or is it meant to be related to some holographic considerations in some way?
So this is valid for systems. I mean, the geometric story is well defined in any number of dimensions, it's 1 + 1 or greater. I think at the level of defining a generating functional for transport coefficients, that's the part I would say. If you have a condensed matter system where Galilean invariance is a good symmetry, so for instance, a metallic system with a large amount of electrons, so that kind of any underlying lattice structure is basically screened away, then indeed, these symmetries should be good effective symmetries of that system. But it's really just in a sense of constraining how the system can kind of transport energy and charge, and et cetera. Your question about holography is very interesting. Something I didn't get to talk to because I didn't have time to go into detail about the Newtonian gravity part is the following. So, let's see this. So Newtonian gravity was the case where if I set my giant mess of torsion to 0, then Newton's equation for gravity covariantly is just r mu nu is 4 pi Gn mass density n mu, right? And this is nice as an equation of motion and it's invariant, but for instance, we don't have any method of getting, I don't know, I'm sure there's a way of doing it, I don't know how to derive this or some sort of generalization of it from an action principle in the way that you can just write down Einstein, Hilbert, or Palatini and immediately get vacuum Einstein equations, right? And to do something like a holographic story, you really need as a starting point a good action principle, because in holography, you usually end up saying that the approximation is that e to the minus classical gravity is equal to the generating functional for the CFT. And so just knowing what the geometry is a useful start. You could ask questions like, say I want a holographic system that's dual to a non-relativistic conformal theory, so a system that has Schrodinger symmetry, then the usual question would be, I need a kind of, let's say you want a 5-dimensional geometry whose isometry group is the 4-dimensional non-relativistic conformal symmetry group. I'm sure that the answer to what that geometry is known in the literature, but I don't know what it is.
Just one quick follow-up question. If you take a gravity theory, Lorentz invariant,
Yeah.
usual general coordinate invariant, gravity coupled to matter,
Yeah.
can you take a limit in that setting
Yeah.
to derive the results that you have here? Here, your approach was to start from the bottom to build it up
Yeah.
nicely, geometrically.
Yeah.
There's no limiting procedure really. as
There
such.
is in this particular case, and this is, I mean, and that part of the story is not new, right? This stuff was developed very nicely by Parvathy, Duval, Kunzel, Ehlers, and other people whose names I'm forgetting at the moment. You know, starting even with Cartan, right? Cartan wrote the first paper on covariantly doing Newtonian gravity. But that is a particular special case, and our motivation is we want to understand energy transport, and energy transport just doesn't fit in just Newtonian gravity.
No, I mean gravity coupled to stuff, you know, like scalars, vectors.
So you need torsion.
So you can, the
You need
problem is,
torsion.
well,
Bosonic torsion,
You need torsion.
is that a problem?
no, so you can do it, and that's what I was writing down. So, you know, I told you how to go from Klein Gordon to Schrodinger by just a rescaling. But that was, again, very specifically for Newtonian gravity. But you can't, right? So you can take matter fields and take their c goes to infinity limit on Newtonian spacetimes. And similarly, I didn't have it, but it's very simple. I can show you quickly later. How to go from an ADM decomposition of a generic Riemannian manifold, and you have to make some assumptions about c scaling and the lapse and the shift, as you would expect. But with those assumptions, you can easily take c goes to infinity and recover the Newtonian spacetime very quickly. And I think that's, I'm not going to remember the wrong person, but that, yeah, you can definitely do that.
Thank you.
But yeah.
All right, let's thank Matt one more time.